Hello, everyone, and thank you very much to the organizers for giving me the chance to present this talk today. My name is Emilie Hertig. I'm a PhD student at the University of Cambridge, and I work on several aspects of early universe cosmology. Most of my PhD work has been on CMB analysis and inflationary physics, but today I will be presenting another project I've been involved in more recently as a member of the QCMFP consortium. QCMFP stands for Quantum Simulators for Fundamental Physics. Its goal is to develop quantum analog experiments to simulate both black holes and early universe dynamics. Here in Cambridge, we have several members of this team. First, we have Hiranya Piris, Alex Jenkins, who is also giving a talk at this conference, as well as Zoran Hadjibabic, who is our experimental contact at the Cavendish Laboratory. Now, I'll give you a very brief introduction to the phenomenon that we are aiming to reproduce, false vacuum decay. We are considering a relativistic scalar field with the following equation of motion and a potential that has a local metastable minimum called the false vacuum. Now, in a classical system, this local minimum would be a stable equilibrium. But in a quantum system, it is possible for the field to locally transition from the false vacuum to the lower energy global minimum. And this process creates an expanding bubble of true vacuum. It is a highly non-perturbative, non-equilibrium process. There are several fundamental questions that motivate the study of false vacuum decay. The first one is directly related to the origin of the cosmos itself. Indeed, if the inflaton field has a metastable potential, then it is possible that the birth event of our local universe was a false vacuum decay process. In other words, our universe could be a true vacuum bubble expanding within a much larger, eternally inflating multiverse. The second motivation relates to the composition of our universe, in particular to the matter-antimatter asymmetry. In several extensions of the Standard Model, the electroweak phase transition is strongly first order, and CP-violating processes at the bubble walls create the baryon asymmetry that we observe today. The third motivation is directly relevant to our present universe. Indeed, measurements of the Higgs and top quark masses seem to indicate that the Higgs is just in this really interesting region of parameter space, right in the range of metastability. This might mean that the Higgs is not currently in its true vacuum, and that false vacuum decay may be looming in our hopefully very distant future. Observationally, if a first-order phase transition happened in the very early stages of our universe, it may have left potentially detectable signatures, both in the statistics of the CMB anisotropies, in the distribution of large-scale structure, but also in the form of gravitational waves. So these quantum simulator experiments and the numerical efforts related to them are a way to predict such signatures and to set new targets for upcoming very sensitive CMB and gravitational wave observations. Now, moving on to some theoretical background, false vacuum decay is traditionally described as a tunneling process in Euclidean time. It does not have a classical description, so we go to imaginary time and use the path integral formalism. So the solution will be the one that minimizes the Euclidean action shown here that we get from the relativistic scalar field Lagrangian. This gives us the following equation of motion. Now, to solve it, we assume OD+1 symmetry, and we set the relevant boundary conditions to ensure consistency at rho equals 0, as well as locality of the phase transition. And our solution ends up looking this way. This is for just one spatial dimension. Here in the center of the bubble, we are close to the true vacuum, and as rho increases far away from the nucleation site, we go back to the false vacuum. And the field profile along these radial coordinates can be solved for, because now this equation of motion is very familiar. It is simply the classical path of a particle in the inverted potential, going from this hill here at rho equals 0 and settling at infinity on top of this lower hill. So now to get the real-time evolution of this bubble, we take a slice straight through this solution at tau equals 0, which is also t equals 0, and this gives us the field profile at nucleation time. After this, we can analytically continue this solution in real time. So this field profile can be approximated as being close to the true vacuum at the center, and then having a wall at a fixed Euclidean radius, separating this bubble from the false vacuum. And going back to real time with the sign change, this becomes a hyperbolic trajectory, with the bubble wall ending up expanding close to the speed of light at late times. So the instanton formalism gives us both an estimate of the late time evolution of the bubble, and it also provides an estimate of the decay rate, which is the probability of a bubble nucleating within a certain amount of time. But there are several really important things that it does not tell us. First, the real-time dynamics of the nucleation event. But also, it does not tell us what happens in an inhomogeneous or expanding spacetime that does not respect the restrictive symmetry conditions. And more importantly, it does not apply to configurations with multiple bubbles. And this is especially important to understand because clustering effects and bubble collisions are amongst the top candidates for producing potentially observable signatures. So this motivates the development of a complementary approach. And one option that Alex will talk about in his presentation is to study this phenomenon directly in the lab with a quantum analog experiment. Another approach, which is also essential to interpreting the results of such experiments, is to simulate the phenomenon numerically on a lattice. We initialize our simulation with the field in the false vacuum, adding Gaussian fluctuations that we sample using a power spectrum that corresponds to that of fluctuations in the quantum vacuum. And then we evolve those fluctuations classically. So the quantum aspect is all in this first step, and then we solve the real-time classical Hamiltonian equations of motion. And here you can see an example of such a simulation result in just one spatial dimension. And we actually see events of false vacuum decay. We see bubbles nucleating. Now the question is, how well does this approach reproduce the quantum dynamics of the phenomenon? Theoretically, this technique is motivated by the truncated Wigner approximation, which consists of mapping quantum density matrices to classical probability distributions. And that's what we do in the initial conditions. So we capture and we enforce the uncertainty principle in our initial state of the simulation, but then we solve the classical equations of motion, so we do not capture interference effects that would be accounted for in the path integral. We are expecting this approach to be valid at first order in h-bar, which is actually the same order as the instanton approach, which is also a semi-classical approximation, but relies on very, very different assumptions. And we can also check that the spectrum of fluctuations that we insert in our simulations remains stable over typical simulation timescales, so it does not thermalize. It stays similar to that of the quantum vacuum. Here we see the power spectrum of the field phi, and it follows the theoretical expectation here up to the UV cutoff that is represented by the dashed line. Here I've plotted 5 different time slices throughout the simulation. And the same thing here for the power spectrum of the momenta pi. It does not change significantly with time throughout the simulation, and we still have the distribution expected in the vacuum. Now, as we expect this approach to be a good approximation of the quantum dynamics of false vacuum decay, we would then expect the decay rates observed in lattice simulations to match the predictions from instanton theory. However, this is the actual results that were obtained a couple of years ago by Jonathan Braden. This phi zero, you can read it as quantifying the impact of the fluctuations. So with decreasing phi zero, we have more intense fluctuations. And on the y-axis here, you have the decay rate. This blue line is the prediction from instanton theory. And those green points here are the measured decay rates from large ensembles of lattice simulations. And you see the mismatch is really obvious. There is a clear discrepancy, and the lattice results are much higher than the prediction. So where does that come from? What does it mean? Well, one first insight into what could explain this is the observed dependence of the decay rate on the UV cutoff of our simulations. Here, the axes of this graph are the same as the previous one. And these are lattice simulation results for 3 different values of the UV cutoff. So progressively including more and more fluctuations and shorter wavelengths of fluctuations in our simulation, you can see that the decay rate increases with that UV cutoff. So there must be something related to the impact of fluctuations. And this means it's very likely that the discrepancy is explainable by renormalization effects. Renormalization means that the bare potential that we give to our simulations is not actually the same as the potential that should be used in the instanton formula when comparing with theoretical predictions. Because the instanton approach is applied to the mean field or to long wavelength modes. So to be able to make a real quantitative comparison between the two, we need to understand how to relate the simulation input, the bare potential, to the potential that is felt and experienced by the mean field to be able to compare to the instanton approach. So how do we do that? This was started by Jonathan Braden. Here's the bare potential that we work with in our simulations with the false vacuum here, the true vacuum here. Now we look at the mean field equation of motion. So the gradient term disappeared because the mean field is spatially homogeneous. Here we have the time variation. And now we average this derivative of the bare potential. To obtain an expression for this, let's consider our fluctuations. So as I said in our simulations, we approximate these vacuum fluctuations as Gaussian, and the variance of those fluctuations depends on the power spectrum that I was showing earlier. So it depends on both the effective mass of the field in the false vacuum and on our UV cutoff, as well as on our infrared cutoff, which is just the fundamental mode of our simulation. So that's the parameters that it depends on. Now we can, in the symmetric minima, so in both the false vacuum and in the true vacuum, we can Taylor expand our derivative of the bare potential. That's essentially the negative of the effective force felt by the mean field. And saving you all of the tedious algebra, here's the final result in this case for this potential. So we see now that we have an expression for the effective force that depends on the mean field and on these parameters. And now what this gives us is the effective mass. So the curvature of the potential in the symmetric minima gives us a mass for the field. And once we account for the effect, once we sum over the effect of all these fluctuations, we see that the curvature has changed and the effective mass can be obtained. So we can solve this equation for MF. It appears on both sides of the equation. So we solve for it numerically and we get an estimate of the effective mass self-consistently in those symmetric local minima. But that does not give us the full shape of the effective potential. That's only a valid approximation in those symmetric local minima, not in the region in between, which is important to fully predict the decay rate. And here you can see an example. If we have one free parameter in our effective potential, even though the curvature in both minima is fixed by this calculation, there is still a range. For example, here we've varied the energy splitting between the false and true vacuum. There is still a whole range of potentials that have the same curvature, but a different shape in between. So this needs to be determined more accurately. Now, interestingly, this renormalization, this mass renormalization scheme is in qualitative agreement with what we observed in the lattice simulations, because as you can see, it leads to a lower curvature, so a lower effective mass in both the false and the true vacuum, which means that the decay rate will become higher because effectively this potential barrier between the two vacua is lower, so that leads to higher decay rates. And if we increase the UV cutoff, we take into account more fluctuations, so this effect becomes more pronounced and the decay rate increases. So the agreement is qualitative for now, and to make it fully quantitative, we need to be able to constrain the shape of the potential more accurately. And that is the ongoing project that I'm involved in. So here, the idea is to reconstruct the effective potential by probing the bubble profile, so the field profile at the nucleation time, extract that from the simulations and backtrack to understand what the shape of the effective potential is. Here you can see the bare potential prediction, so the predictions for the instanton field profile. Now, if we take into account renormalization in the same parameter range as the plot on the left, this is what the vacuum bubble profile becomes. So you see that it becomes a bit more similar to the thermal profile, a bit lower, slightly wider. And this, if we can observe it in our lattice simulations, then we can constrain the shape and get more information as a first step towards a quantitative comparison with instanton. So that's what I've been working on lately, is extracting bubble profiles from those simulations. First, we need a criterion for bubble detection that gives me the shape of the bubble at the late times. And from this, I find the symmetry axis of this bubble. So basically, the only assumption we're going with here is that at late time, the bubble is expanding symmetrically with the walls growing at the speed of light. Now, at early times, this bubble is not symmetric. We see the fluctuations, we see the nucleation starting to happen here, and it looks like it has a really large negative velocity. And that means we need to put this bubble back into its rest frame. In the simulation frame here, the bubble is going fast, and that's something that's been observed in the past by Dalila Prevru at the Perimeter Institute. She worked on thermal vacuum decay and had a first version of a bubble detection and deboosting algorithm. Here we've improved it because in the vacuum case, bubbles tend to move at much higher speeds, really close to the speed of light, actually. So that means that moving from that simulation frame to the bubble rest frame to have an accurate estimate of the bubble profile is really, really important. So the way we develop our deboosting algorithm, because our lattice code is a pseudo-spectral code looking into the Fourier modes of the field and evolving them in time, we also rely on Fourier transforms. So this is the 2D Fourier transform of my field here. Now, we apply the Lorentz transformation, so we transform our grid points in the simulation frames to grid points in the boosted frame with a given velocity, and we evaluate the Fourier modes of the field on those new grid points. So that removes the need for any kind of interpolation. So we compute the residuals between one side of the symmetry axis and the other, and minimize those residuals iteratively until the bubble is as symmetrical as it can be, and we take that as the final boost velocity. Now, here you can see some examples. So that's the bubble I was just showing. It is actually quite difficult to figure out where the nucleation time is. We can see very clearly the expansion, the symmetrical expansion at late times. But in this zone here, what is the precursor and where do we really consider the bubble to have appeared? This is actually hard to tell. Here I've plotted a few time slices. The blue one at t equals 0, clearly we don't have a bubble yet, we're just in the vacuum fluctuations. This red one here at t equals 12, we clearly already have a bubble with a sharp expanding wall. But in the middle here, in these orange and green slices I've plotted, where exactly do we consider the nucleation time? This is actually impossible to tell for just one realization. So to be able to measure that field profile to compare with the instanton prediction, we need to stack many realizations. Here you see another realization, same conditions, same simulations, just different random initial conditions, and the time slices look quite different. So the work that is now ongoing in Cambridge is to produce a large number of these realizations, use that deboosting, iterative deboosting algorithm, and get those simulations synchronized and stacked. So using the evolution at late times, we synchronize them, stack them, average them. That will then be much more accurately determined than in a single realization. So for the future prospects of this work, the most exciting prospect, of course, is the experiment being developed in Cambridge. The goal is to observe a vacuum decay fully triggered by quantum fluctuations, not thermal ones. That would be the first time this is observed in a Bose-Einstein condensate. Thermally activated false vacuum decay was realized not too long ago in a ferromagnetic superfluid. And now for the fully quantum process, we are hoping to have first results by March of this year. So this is a really timely work. And I won't be giving more details on the experiment because this is all in Alex Jenkins' talk. So please do watch this talk as well. And just to show you the current status of lattice simulations, these are 2D simulations, so 2 spatial dimensions, and you can see the time going as the movie. On the left, you've got the Bose-Einstein condensate. On the right, the scalar field simulations. And remarkably, a bubble has nucleated in about the same amount of time and at about the same place in both. So that goes to show the quantitative analogy between that quantum system and our scalar field in the vacuum. Now, there are some key differences in the left panel. More bubbles have nucleated after the first one. So it seems like there is some key differences we need to understand before we are able to quantitatively interpret the experimental results. And again, this current ongoing work on renormalization will be key here, because as you can see, and you'll see those plots in more detail in Alex's talk, but the quantitative analogy in the power spectrum of fluctuations between the Bose-Einstein condensate and the Klein-Gordon scalar field works up until a certain wave number, but at a shorter wavelength in the UV, while the Klein-Gordon field fluctuations would be going down, the fluctuations in the Bose-Einstein condensate tend towards the non-relativistic white noise kind of power spectrum. So that means there are effectively more intense fluctuations in this part of the spectrum. And as we know, renormalization effects tend to increase decay rates. So this is an indication that the key difference between those 2 panels might also be explainable by renormalization. So the next steps in this theoretical work now is to work with those stacked bubble profiles and have an answer as to whether our simulations really capture the same decay channels as the instanton predictions and how to relate the 2 quantitatively. Then extending those findings to 2 spatial dimensions so that after March of this year and in the next few months, we can actually start interpreting and understanding the cold atom analog experiments. And after this, the idea is that the experiment is a way of calibrating and understanding the range of validity of the numerical simulations in a controlled setting, and to have a confirmation of our theory in a system that really shows all the quantum effects. And once we have that, if we know we can trust our simulations, we can then change and add complexity and go to higher dimensions, more complex potentials, expanding space-time, adding gravity, all those things that could make it more realistic to predict observational cosmological signatures, such as, for example, a stochastic background of gravitational waves. There have been some predictions for gravitational waves emitted in thermal phase transitions, like in electroweak baryogenesis, not so much in the vacuum case that would be relevant, for example, for eternal inflation. And effects such as bubble clustering might be key to understanding the shape of that spectrum and the energy scale of it. There can also be signatures of bubble collisions in the CMB. These would be in the form of localized long wavelength modulations of CMB temperature and polarizations. And these are all very exciting prospects and future synergies with upcoming cosmological observations. If we can get an estimation of nucleation rates, of the dynamics of nucleation in real time, and the dynamics of bubble collisions, then we can make new predictions and set new targets for the really sensitive instruments that are coming up in the next few years and in the next decade. For the CMB, we've got the Simons Observatory, CMBS4, Lightbird. For gravitational waves, we have LISA that has just been approved, as well as atom interferometers that will probe the gap between LIGO and LISA. And all of these really sensitive observations will then be able to set new constraints on the characteristics of early universe phase transitions and hopefully help us unveil the origins of our universe. Thank you for your attention.